And who is that? Yao, is that you?
Yes, how?
But you've not been coming, Yao. You've not been coming for these lectures. You are away.
I'm always in class, sir.
You are
Yes.
Benjamin Yao Sefabani.
Sure. I'm always in class.
Okay, I will determine that. Is that okay?
Okay, okay. Anyway, I'm using my phone, so that's the name of my phone. But when I use my laptop, it is Ben.
Okay, I'm so okay. I know you has been here. Okay, that's fine.
Yeah.
All right. Okay, you're safe now. Let's go on. All right. So like as I was saying, going back to the slide, networks are everywhere. What we are looking at right now is some kind of drainage network. So think about it. All the flooding issues that we have in Accra. Unless you've not experienced it before, I experienced some flooding in my own house. You know, it wasn't like flooding within the community. Are you all right? Within the neighborhood, it was just flooding within my house. In other words, the drain network within the bigger compound wasn't okay. Are you all right? We can have bigger drainage networks in channels connecting to each other. So take note and underline the word connect. All right. And we can look at this one is London Underground. Okay, if you haven't been to London before, it's not a big deal. But the different colors of lines indicate different trains, yeah, as in vehicles, moving on these rails from one point to the other. Okay, so once you are on the, the brown line, then it means that you are moving and you are actually traversing and visiting certain, places. I think the names are not clear, but you can see that these are train stations, all the dots, the round dots. Are you okay? All right, so that is a network. So by now, I think you should be understanding. Please try and understand it. When I ask you a question, you answer it the same way I'm explaining to you. I'm not rushing, taking my time talking about it. And I'm saying this because of some of the answers I saw in the exam. Basically, that's the real network over. Let's look at this one. This one is more of a power distribution network. And I mean, and you also see a gas pipeline network on the left-hand side. And on the right, you also see a road network. Are you okay? I'm still using my phone for this presentation. Forgive me, but honestly, I've lost my laptop and this is the only way to do it now. So I hope you can see it anyways. Here we go. Road network, that's the road you see is starred over there, and it's helping us to get to one place. Okay, and then we need to connect to one road through the junctions. Are you all right? Or interchanges. You've heard of interchanges. All right. Power networks, we need to carry power from one point to the other. Are you okay? So it goes through poles, light voltage, high voltage pole, high tension pylons are connected. So there's a whole lot of connection going on. So take note of the word connect. There's a connection going on. Now we need to share, the gas or something like that. Then how do we do it? We just take one pipe and take it to every house, okay, in a sequential, in a series. So the pipe goes through your house and gets to the next house, and then on and just follows a path. Are you okay? You're gonna take a long time for you to get your own gas. It's gonna cost you a lot if you went that route. Are you okay? So networks are around us. Is that okay? Now, the most important thing to do with networks is to really analyze them, because if they're not analyzed, you don't make the best out of them. Are you okay? In other words, we look at our condition, we look at our road condition in Accra, the traffic, congestion, and the first thing that comes to people's minds is that people are buying cars. There are too many cars in Accra. That may be true, but actually, you'll be surprised that if we really improved on our road network, we may realize that we don't even have enough cars. Because how many people have a car per household on average? Only a few. In some houses, nobody even has a car. Are you with me? So there's a need to analyze your network. What if you could do an analysis of the traffic and then know exactly the route to use in one afternoon around 12 o'clock? That would be nice, isn't it? What if you could do a network analysis and know that in a certain particular area, if we actually kind of strict of the save some money. Are you okay? I'm talking about power distribution. How do telecommunication networks, the telcos, how are they able to determine where to place the next mast in that network? Are you okay? And the reason why we call MTN network a network is okay. I don't know what the M and the T stands for, but obviously all the telcos call themselves networks. Are you okay? How do they know exactly where to place the next mast so that we can improve on the signal? That kind of analysis can only be done if we have a network, okay, and we're analyzing the network. Okay. Now, what are the prerequisites for that? To have a system that supports that analysis. Sometimes we need real time. Are you okay? We need a system to be real time. And so we need to have very accurate data, all right, to support that. Okay. We need a system to be compact. That means that a system needs to be up to date as well. Are you okay? Then also, from time to time, we need to have address conversion function so that we just get to know exactly where we are in the network. In that case, then you need to have data which is topologically correct, obviously. Are you okay? Now, there are other system requirements and data requirements where the output display or synthetic voice display can also be used. Is that okay? We can talk about several attributes. Are you okay? Because you see that when you actually work with networks, the system that allows you to really analyze it and understand how it works should be able to give you an output. And because of that, we will need things like, for example, if it's a road network, road condition. Are you okay? Can talk about classification of road, speed restriction. Okay, you can also look at it in terms of flow. Are you okay? How fast do we get water flowing? Are you okay? We can look at, I think everything we're looking at here is really about roads. Yes, I must admit. Speed restrictions, one-way streets. Are you okay? Which direction are we having vehicles to move in a particular direction? Turning restrictions. Sometimes you can't do a U-turn. It's all right. And you do that and the police gets you and you're in trouble. Are you okay? And sometimes I hear they hide behind some trees and watch you as you make the mistake and they can arrest you. Very bad, isn't it? All right. So we need to also get the width and height restrictions. There are certain points where certain, trailers, articulated tracks cannot pass. Are you okay? So we need to get all that in. So as a civil engineer, in your design, you need to be, conscious about this, that it's not about you just thinking about substructure, whatever, how to construct the road, are you okay, and strength and whatever that soil tests. You should be thinking about how the parts are going to work together. Otherwise, in a way, you fail. Or you have to know how to work with other professionals to make sure that your design is perfect and is optimized. That's the word, optimized. So we need to know the junctions. Also, where do certain roads meet? Where should certain roads meet? Runabouts, we need to know. Runabouts are treated as junctions if you know how to drive. Are you okay? Reference landmarks, we need to know where we are in terms of location. Okay? So network analysis. Are you okay? A network, what is it? What is it? A network is one of 5 basic entity types. Okay, so in other words, you can look at other entity types, but for now, network can be looked at as just one of a set of entity types. A network can be defined as a set of linear features through which resources flow. Set of linear features through which resources flow. Okay, so in other words, for every network, it's like as if you have a line joining 2 points. So it's like me getting up and saying I'm going to Western region or something from Medina. I only see myself traveling along a line, a path, a road. Are you okay? All right. So that we should think about that linearity. Are you okay? Modeling it as a line. So in every network, there are lines. Are you okay? Now the next keyword there, I think we met this word before, is a node. And the node is the endpoint of the line. I think we already talked about this. And the nodes are used as origins and destinations. In other words, I'm starting from Medina, I'll end up at Kaso, I'll end up at Winneba, I'll end up at in some, these are nodes, the beginning and end, but in between, there's a whole lot going on. Are you okay? In between, there's a whole lot happening. Are you okay? Now, we talk about links, we talk about nodes and links. In fact, some also refer to it as edges. Instead of saying lines or links, it can be also referred as an edge. Okay, so take note of that. And links traverse from one node to the other. So we start from one point and end at the other. So the network is basically made up of just nodes and links, node and links. And of course, the nodes are connecting. Are you okay? Connecting from one line to the other. So to connect from one, I think we talked about this in topology. Are you okay? And you realize that with network analysis, if the data is not topologically correct in terms of connectivity, then we cannot even carry out the analysis. Are you okay? I says that nodes can have properties, but in network analysis, we are usually more concentrated the characteristics of the links. Yes, so we can actually have the nodes are really like the junctions, which are really helping to connect. Are you okay? And one of the properties of the nodes will be just the name of the node. It's like a junction. What do you call a junction? Malam junction. Are you okay? Clapham junction. Are you okay? Etc. All right, but we are saying that we can concentrate more on the line and then their properties. One of the properties of the line, the link, or the edge in a network is the length of the line. Okay, so if I'm traveling from one point to another point, I'm interested in how far I'm going on that line from one node to the other. The direction. I may also be interested in which direction am I going to flow. Are you okay? So if I'm doing analysis and then there's a flow of gas from one point to the other, from north to south, then it does make a lot of sense. So it's very relevant to know the direction because it will affect the final result of the analysis. Connectivity is how, of course, the lines connect. Are you okay? And we are saying that they connect by the nodes or the points. And we can also look at the patterns, how the lines are actually like arranged in terms of density and how they've been grouped as well. Now, when you look at network analysis, then you can have four main types. Are you okay? As indicated by Lorini and Thompson, 1992. We can look at unoriented networks. Are you okay? So no direction. We can talk about oriented networks. Are you okay? Which means that there's a direction. Unoriented with loops. So some networks never close. It's that you start from one point and you just go and you never come back on that path. Or there's no kind of looping. If you know what a loop is, it's kind of closed like a polygon. Are you okay? So we can have oriented but with loops. Okay, so these are just terminologies that it's very easy to understand. In terms of pictures, you can look at this one here. So we can have unoriented network. So there's no direction. Okay, you look at this corner here. So an unoriented network, we have actually connected nodes together, linking the links, yes, or the edges or the lines, but then there is no direction. Okay, we can't tell where things are moving. Things can move anyhow. Are you right? More or less, that's what it says. We can have the oriented network. There's a sense of direction here. Are you okay? Then, but of course, it's not looped. So the top two are not looped. But when you look at the bottom, then we can have unoriented loops with loops. Are you okay? So here, it's not oriented, but then it's looped so that we can move from one node and come back and go back again. Are you okay? Whereas at the top, we can be moving from one point to the other and we may not find a way to, connect, but I think that we really prefer the oriented loops. There's a lot of resources that can be shared with the oriented loops. Are you okay? So that is very important to understand. Now, I introduced a new word. Maybe you don't know this word. There's a word called algorithm. Okay, and we want to look at in every analysis, there is the need for a program. There's a need for a certain procedure to be carried out as part of the analysis. Okay, normally this is actually implemented in software and computer programs that allow you to now do the analysis. Okay, so all the things that we are doing in all the software that we're using as engineers, all of them have some sort of procedure under it. Okay, that do this first, do that, and then if this value is like so, do the other one. Are you okay? Now, so at the heart of every network analysis is the search. Are you okay? Procedure. In other words, we're actually looking for something. And what are we looking for? Are you okay? What are we looking for? Sometimes we are looking for a shortest route. Sometimes we are looking for how far we can reach within the network. In 5 minutes, where can we get to? Everybody, where you are now, where can you get? If we were actually in the face-to-face, lecture, I think using the Zoom, I mean, there flexibility is there. But in 5 minutes, where can you get to? And if we were to look around, you realize that there are about a couple of places you could reach. Are you with me? At the heart of a network analysis is the search procedure. So the word procedure there is referring to step-by-step way to get something done, to find something. Are you okay? And that is what all analysis should do. There should be a finding at the end of an analysis. Are you okay? So, for example, we can select links that take you as far away from the start node as possible, never turning back. Okay, so that you can even think about this for a while. Yeah, as a student, you can think about it. You can have discussion with your colleague and find out what does this statement mean. Are you okay? I want to do an analysis. I want to see, the links. When you say the links, for example, imagine that you're on a road and they're saying that show me the path that I should take. That would take me very far from my start node as possible. Which node would take me very far if I go on it? Are you okay? Without turning back. Are you okay? So that is one of the things that we could be looking for. Alternatively, one can search all the links that propagate from a node, moving out one link at a time and gradually accumulating a cost of travel in all directions from a start node. So sometimes you are interested in, if I were to travel from here to Accra and then come back and go back to Kaswa and come back and go back to Koforidua and come back. Sometimes we look at tipper trucks. They face this problem all the time. And remember, tipper trucks are all part of civil engineering. Are you okay? Let's face it. Transportation, getting material to the site and all that. Yeah, construction and engineering, they are together. Are you with me? Every construction project is with our team. So as an engineer, then you should know that the costs of the project is also part of engineering. Are you with me? And so if they are to move, the truck is supposed to move a certain number of times and you are actually preparing an estimate, how do you actually arrive at it? And there's been a lot of cutting corners going on, isn't it? Because I'm sure that people are hearing this for a first time, but they've been working for a long time, for many years. And of course, so if we were to do due diligence, I realize that a lot of people have cut corners and made a lot of money just because the right thing wasn't done. Are you with me? If I'm to move from one point and accumulate the cost, how much am I looking at in terms of, okay, the cost, total cost? Okay. One can also seek to find a route or a route that passes through the fewest number of nodes, even if it is not necessarily the route of the lowest cost. Okay, so in other words, in some country, most advanced countries, okay, guys, that called, so here's a pause. Yeah, so he's checking on me. I think if I were using a laptop, I wouldn't have this. But it's okay. Let's carry on. Yeah, good for me. Yes, he's sending me some cash. Anyway, so here we go. If you want to find out the route to Kumasi without stopping a lot of, or without coming to, if you've actually traveled between two cities, Kumasi, Accra, one of the most annoying things is that you get to a place like in Koko or something, and it's like you ask yourself, is this my destination? Because virtually you are in the middle of the central business district, and the whole place is just jam. They don't even know that you are traveling from Accra and you're that side. Are you see? Oh, yeah, traveling from Kumasi and that side. Okay, so of course we need to be able to do such analysis to tell us where to pass when we have the option. But when you don't have the option, well, what do? You don't. And that is why we have this multi-hierarchy, transportation system where you can actually travel, from one point to the other without actually meeting any junction at all. So I hope you are paying attention and making notes and you are following. But what I've said here is now to set 5 questions. Are you okay? I've said a lot in this particular slide. Please. All right. So now that brings us to an algorithm. I think it's because I like programming. That is why I have actually spent a lot of slides on one particular, algorithm. Okay. So the algorithm is actually the step-by-step procedure that is required to create a computer software or program. Are you all right? Every engineer should know some programming. Are you with me? So now, this one is called a distress algorithm. So distress algorithm in network analysis, that's only one thing. Even though there's a lot of analysis that can be done, I think I'll mention a few that may not be found on this slide. But now let's start with the distress algorithm. Are you okay? So the question now is that, what is the shortest path between here and I need to go to AFSA, which is the new Barclays Bank? Yeah. What's the shortest route? Okay, the suggestion, if we were to even have the argument, we like arguing a lot, as Ghanaians, we like to always challenge each other in an argument, a discussion. What is the shortest route to Accra? Or someone will say, go through East Legon and use the under bridge, and someone will say, no, go through Shiashi, and then we can kind of argue and argue. But that problem is solved via an algorithm, via a computer program, we're not even going to talk about software. The algorithm is a procedure, and then you can implement it in different ways in the software. All right, so most of the time, this is one of the things you want to find. In fact, I use this a lot. Since I didn't really grow up in Accra, I always like to use my Google map and then find the shortest path. And then I get a blue line that indicates the shortest route from where I am to where I need to get to. Are you okay? All right. So that problem is solved by Dijkstra. And how did Dijkstra go about it? So Dijkstra's algorithm works like as shown on the screen. Okay, the idea is to move from point A to point G. Let me zoom in a bit. So I want to move from point A to point G. How would I do it? How can I visit G? What's the shortest route? What's the shortest? The shortest route, according to Dijkstra's algorithm, is to simply move from point A and then visit all the nearest nodes, and then record the cost, how much it will cost me. Now remember that a network is not necessarily a road network, but then so let's recognize that this could be a pipe network. Okay, so let's have that open mind. So we check from A to B, and I realize that the cost is 3 units. Could have been money as well. Sometimes it cost is more expensive to travel between 2 points. We can look at it in terms of money. So the value, the cost could be money, could be distance. Are you okay? Could be anything else. Look. So now A to B is 3. Then the algorithm also checks from A to C, and the cost is 2. So the algorithm assumes that the shortest route is actually A to C, because that is the cheapest. Okay. So we are trying to find the shortest route or the least cost route. All right. So A to C become the shortest. Then we get to C, but we still remember that A to B is 3, isn't it? All right. Now we start visiting the next node from C. Are you okay? We also check the next node from B, how to get to J. Are you all right? So now from C, we can add 2 to 2 and get 4. So that is ACB. Are you okay? So that'll give us 4. I wish I had a pointer, but it's okay. Please, guys, try. A, C, B will give us 4. A, C, B will give us 3. So you can see that we're getting a short route there. It's like a shortcut. It's, for now, after we take the next node, it's actually A, C, B. All right. So that's giving us 3. Meanwhile, we're still at B. It's costing us 3. So I would like to go through A, C, D for now. Then we add another node. Okay, so I'm at D. I'm rejecting A, C, F because that will give me 6. That's too expensive. Are you okay? Right. Okay, so now I now go from B, 3 plus 2, 5. So I'm rejecting that route. A, B to D, that's me 5, too expensive. I'm getting 3 from here. When I take 3, I use 3 junctions. Are you okay? Or 3 nodes. NODES. So this is how the algorithm works. It keeps on rejecting the links and selecting links that will give it the smallest or the least accumulated cost. Are you okay? All right. So you can see that here we're choosing. There's a table, of course, to guide you with the accumulation. And as we move on, here the brown lines have been selected to be the links of interest. Are you okay? So we selected link A to B. Here the alphabets are gone, but if you look at it, these are the links that we selected. A to B, A to C. Okay. And ones that are finally selected, collect B. So here we can see that the cost to B is 3, and then of course to C, okay, is 2. Okay. So that is the table you see on the right hand side. Okay. All right. And then we keep on and on and on. So here we've selected this node to C because it's the cheapest because 2 is less than 3. Are you okay? And so C has been selected. So you see on the right hand side that the table also keeps on. Because we are really doing addition. Are you okay? We are adding cost. That's all. It's not very complicated. Are you okay? No integration or differentiation here. All right. Then we keep on adding. Remember, I told you that we will now be considering other links. And then we want to compare the amount that we get. 6 is not good to F. Yeah. Destination now here is F. It's not going to give us a least cost. So we are still sticking with the C. All right. And then off we go. And then we keep moving on. And then now we are selecting. Yeah. So the green is the one that we want. The brown is actually being considered. It doesn't mean it's been selected. And then we keep on and on and on. So we are considering more nodes. So now 3 is green because to see the cost is now kind of from A to B. Let's go by. I think the letters are really not helping. From A to B, now 3. That 3 now can compare to A to D. As if now that path should also be considered. Are you okay? All right. So then the brown lines are selected. Are you okay? And then we now have, the final route. Are you okay? Why are we going for this route? Who is talking? Who is talking? Who is talking? Don't talk. Yeah, we have 10 minutes. So let me just see. Please mute your mic. All right. Okay. So now we are selecting this final path. Are you okay? Which is actually, let's check the letters. I think this one I should have. Yeah, the final path now is A through B to G, and the cost is 5. Well, because when we move from A to C to D, we had 3, and 3 plus 3 is 6. Okay, so 6 is higher than 5. So even though we rejected A to B in the initial analysis, when we started from here, you see, 3 wasn't really the approved, but eventually 3 becomes the actual root. So it's a repeated something, an iteration. Okay, that's a word. We iterate, we keep on comparing till we get to the very end of the distress algorithm. We can do the reverse. Everything that you see in here, okay, is can be reversed from where we've reached to the G back to A where we started from. Are you okay? All right.